Okay, what we're going to do now is just go through the four properties that we're going to see of integrals. There are others that we'll see more much later on, but these are the ones what we're going to use actually now a little bit, and the others we'll use later. So here's just the first couple. The first thing I want is the property that says that the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. Now, why would that be true? Let's just look at the underlying picture. We've got this function f of x. We're talking about going from a to b and then b to c. The integral from a to b is just that area. The integral from b to c is just that area. And when you add this area to this area, you get the area from a to c. Well, that's all it says, right? So that one is like water. It goes very, very nicely. You get to use tons, which is great. It's easy to understand. You get to use tons. Awesome. The next one's a little bit weird, but it's also equally useful. It goes like this. It says the integral from b to a of f of x dx is equal to minus the integral from a to b of f of x dx. Well, why in the world would that be true? Well, there's really two ways to understand this. Remember that we have accumulating functions, accumulating area from usually a forward, right? This one's going backwards. This one's the decumulator, this one's the accumulator, and they should be negative of each other. Now, if you don't like that, we can start it this way instead. Let's just add the following two integrals. The integral from a to b of f of x dx plus the integral from b to a of f of x dx, like that. Right? Well, we're going to get two things. We're going to get, remember how that other one went? Yes, if you go from a to b and b to c, you're going to get the integral from a to a. Well, how much area is there under the graph from a to a? That's just 0, right? And having gotten 0, I guess I'm going to go to the top of the page at the moment. And I'll finish this line right here, right there. And all I'm going to do is to subtract this integral from both sides. So I'm going to get the integral from b to a of f of x dx, and then we subtract the integral, so I'm going to get minus the integral from a to b of f of x dx. Ta-da! That's not so bad. It does say if you switch the limits of integration, you have to put a minus sign out in front. But it really means this one was accumulating, this one's decumulating. It's a better way to think, and it's probably how they came up with it to begin with. Meanwhile, there's a third one. Third one says, if you look at a function, let's do it, how about we draw the function down here and we interpret up there. Yes, there's our f of x again, like this. And what we want to do is think of from a to b, f of x dx, like that. If we happen to multiply the function by a constant, let's say 2. I'm gonna write c, but I'm thinking 2. Yes. So this is f of x. This is c times f of x. All right. It's just going to be up here like this. How much area is there under the new graph compared to the area under the old graph? Well, the new graph is c times bigger, and there's going to be c times the amount of area. So what happens is, if we're looking at the new graph of c times f of x, we made all the heights, I'm writing c, but I'm thinking twice as high, then what we're going to get is the original area twice as big. Now you notice how we understand this, right, is that we multiplied the height by c, and so the area got multiplied by c. But in practice, that's not what they do. They'll say, you can pull constants out of integrals. which is not an explanation. It does tell us what we can do, but the actual explanation just comes from comparing the left-hand side's area to the right-hand side's area. All right. Now the last one is a property that I've never seen anyone ever get wrong, but explaining it is no fun. So we'll go like this and we'll try to explain it. I want to go like this. I want to say a to b of f of x plus g of x dx. What could possibly happen there? Well, normally people just say, I'm going to take the integral of the first one plus the integral of the second one, which is 100% right, and it doesn't explain anything. Let's just talk about what this is. Remember, an integral is a limit of Riemann sums. So I'm going to say, look, this is just approximately equal to a massive sum, where this looks like fxi plus gxi delta x. Now the reason I did that is so I can distribute on the inside. So I still have sum. I'm going to get fxi delta x plus gxi delta x, like that. Now, what I'm going to do is combine like terms. What we're adding are billions of terms. Each of the terms has an fxi and each of the terms has a gxi. But what I'm going to do is add up all the fxi's first. So I'm going to go, look, this is just a sum. I'm just using the associative law. fxi delta x, like that, plus gxi delta x, like that. And how do we finish this? We finish it the way we started. What is this? This is almost exactly equal to the integral we're looking at. That's the a to b of f of x dx plus, and this is the integral, the other integral we're looking at, a to b of g of x dx. Now, if you had a really strong background and you know how to add two functions geometrically, this is really easy. Most of the time, I haven't seen people be able to do that. So breaking it up into, look, it's estimated by a Riemann sum, break up the Riemann sum, add like terms, and then remember what we're actually estimating is another way to go there. It's a little bit different from the books. The books actually adds the functions, which is great, but if you've never added functions before, geometrically, I don't think their answer is too good. Anyways, those are the four properties.